Hello everyone, in today's class we will discuss the model checking algorithm for CTL in detail. In the last class we effectively introduced the leveling algorithm and how do we calculate the fixed point of leveling for CTL model checker, right. In today's class we will give you the exact algorithm. So, just to recollect, when you try to calculate this, when you develop this CTL model checking algorithm, the adequate set is sufficient. So, in our example, we are basically going to take this adequate set at the start, and what I have to just check, given a property, whether this model satisfy it or not, effectively the start state of that model is satisfying that property or not, right. And the strategy that we have discussed in the last class, that there are one approach could be you take the S0 and check all paths from here, and I will check whether in every path this phi satisfy or not, but that is more complexity is high on that. Instead, what we have discussed in the last class, we will basically label the nodes with smaller sub formulas, and I will identify whether all the states where we can mark with or label with phi, and then I will just check whether S0 is also labeled with that formula or not, right. So, this we can compute in order of V plus E, which is very efficient, right, polynomial time. So, complexity of model checking is not exponential, it is polynomial. So, to do so, today I will define the formal algorithm. I will define two terms, pre for all, pre there exists y, and pre for all y. I will just define this term. This I am going to use in developing the algorithm. Okay. So, y is basically a set of states which is subset of the all states. Okay. Now, so you basically think about I have a states y, right, where there are few states, right, where something is true, and then I try to calculate pre there exists y, right. So, I am saying that it is basically some states S. So, this some state S belong to the sets such that there exists some S dash, right, some S dash here belong to S, and there is an edge from S to S dash, right, and this S dash belong to this Y set, right. So, this then I will say this S is belongs to pre there exists Y. So, effectively what I am calculating here, this pre there exists Y denotes the set of states having at least one successor to Y. It can have other successor, but which is going to some states, but at least one of the successor in Y, right. So, it is basically pre there exists Y, it is basically pre of Y, and it is a existential successor. So, that node has multiple successors, but one of the successor is in Y. Okay. So, it corresponding to the existential next state operator, and we will use this for calculating EX5. Okay, understood. So, it is basically I will identify the states S from where at least there is one state to Y, and from Y I have maybe 4 state. For this I will get something, for this I will get something, I will get this, and this pre Y is all such states, right, for which this is holding. Okay. Similarly, pre for all is the similar thing. Here all successor is going to Y, right. So, effectively pre for all Y denotes the set of states whose every successor is belongs to Y. So, if I take the same definitions or example again, so there are say 4 states here in Y, and for this state S, it has probably say 3 next state, one is going to here, one going to here, one is going to here. Then I will say this S is belongs to pre for all Y. So, it is the definition of pre there exist Y. If one of the successor of this node going to Y, then this will come into this, but here all of its successor has to be from Y only, right. So, this is basically denotes the universal next state operator, and this I will use for calculation of some AX. Okay. So, with this two definition I can write the algorithm for EX5. So, you remember the leveling algorithm EX5 first, where I say that if some state where phi holds, I will try to identify states whose at least one next state where phi holds, then this state I will mark with EX5, right. So, I can use pre there exist, right, because I will mark all the states where phi holds, I will get that x. So, sat means satisfiability of phi, where phi holds, right. So, I will effectively identify all the states where phi holds, and then I will do pre there exist of x, and that will give me these states, right, because I am trying to identify states whose at least one successor is where phi holds. So, then this state, this y is basically my states where ex phi holds, I will return that y. Okay. Understood? So, this is the pseudocode for this algorithm. So, what I am effectively doing, I will identify all the states where phi holds, then I apply pre there exist of x, which is basically identify those states whose at least one successor comes to x, right, and then I will get all those y is basically states where ex phi holds, and I will return that y, right. So, this is our overall algorithm. Find first identify all states where satisfying phi, this is my set x, and compute their pre-existence or predecessor, which is basically pre there exist of x, this give me y, and this y is the states I will return, right, that is the states where ex phi holds. So, complexity I have already discussed, it is effectively find all state phi holds is basically order of v, if I assume the number of nodes is v, and then pre for all is effectively you have to go to each node, and then I have to check all successor, right, and then if the successor is belong to x, I will mark this ex phi, right. So, this is how I am going to do. So, it is basically from each node, each edge I have to check this. So, overall complexity should be v plus e. This I have already discussed in the last class. Now, AF phi. So, for AF phi we have to do this algorithm, right. So, let us see what is the algorithm. So, I identify the states where phi holds is y, right, and x is the all states, right, and then I will repeat until x and y are same. So, what I am doing, I am copying y to x, right, and this is interesting. So, this is what actually happening here. So, then I will identify pre for all of x. What is x? X is basically you are starting with the set of states are phi holds, because you copy it here, right. So, you have the states of states where phi holds, right, and then you identify the states for whose all successor is coming here, because this is pre for all, you will identify these states, right, whose all successor are coming here, and then you are taking a union of this, right. So, this is what I am going to do pre for all of this, right. So, as I mentioned, this need forward BFS. So, forward BFS you are visiting the edges multiple times. So, the complexity would be order of b into b plus c, right. But this is clear what is happening here. So, and then I am taking a union of this. So, whatever the states earlier there and the states I identify through this, and taking a union, and I am saying all these states AF phi holds, and this I will continue until I am not able to add a new state in one iteration, because I am starting with x and y same, right, because I am copying y to x. Now, if this y is not growing here, then after next iteration it will become x equal to y, right. So, this there will be a bracket here, you can see this way, and then return you after once you complete this you return y, right. So, effectively this is what I am doing, initialize the states with phi, then iteratively I add states whose successors are already in this set x, and then you step when you cannot able to reach a new state, that means you reach a fixed point. Okay. The next is SAT of EU phi 1 phi 2. So, effectively this algorithm identify the states where E phi 1 until phi 2 holds, right. So, how I am going to do? So, I will identify the states where phi 2 holds, I will identify the states where phi 1 holds, and this is y and x respectively, and the x is the entire state. And why I am doing this? Because initially this particular set, condition should not satisfy, right. You have the states where y holds, and I am just checking whether x equal to y. So, if all state phi 2 holds, that means in all those states E phi 1 until phi 2 holds, I do not need to go further. But if it is not the case, you go inside and then you basically you make your x equal to y equal to x, right, or sorry, x equal to y. That means x is now set of states of phi 2 holes, and then this is the main part of the algorithm. What I am doing here, I am taking y union. Y is basically a set of states for phi 2 holes, right, phi 2 holes. Then I am taking union of with this. What is happening here? W is the set of states where phi 1 holes intersection pre there exist of y. What does it mean? Y is basically the states. So this is basically your y, right? And now what I am saying is that pre there exist of y. What does it mean? I will find a states whose one of the successor come here, and since I am taking intersection here, means here also phi 1 holes. So effectively this line means, this part of the formula means the states where phi 1 holes and its one successor is going to states of y, right, and then I am taking a union of that. So if you do this, your y is growing, right, x is the initial states, initial set of states, and this become your y now, right, this become your y and this is your x, and I will check whether I am able to add a new states here. If I am able to do, then I will go again here, otherwise I will not continue and come out, right. So this is the, whenever I am not able to add a new state, that means I reach a fixed point, right. So this is effectively the existential algorithm, and this is exactly the leveling that I have discussed in the last class, and I have already discussed the complexity is effectively V plus E, because I am doing a backward VFS here, because I am having existential quantifier. Existential pre can be done with backward VFS, but for all pre cannot be done with backward VFS. So here what I will do, I will basically take a state from here, I will go to previous states, and I will check whether phi 1 holds here, and I will do this. So overall complexity will be, effectively I am for every time I am adding a new node and any edge is not effectively visiting more than once. So the overall complexity will be order of V plus E, right. So start with satisfying phi 2, iteratively add states as phi 1 satisfying, and that have at least one successor already in this set where E phi 1 until phi 2 holds, right, and this I will continue until I am not able to add a new state, and that is my least fixed point. Okay. So the pseudocode of the algorithms are clear now. So if I now try to develop the entire model checking algorithm for CTL, you have all combinations. So I will write this. So if your phi is true, that means I will say true holds in every state, right. If you want to check false, I will say false does not hold in every state. If you have to check if your phi is basically p, some proposition, what I will do, I will check all the states where which is labeled with p, I will return those states. If this phi is not of phi 1, then I will take the entire states and the states where phi 1 holds, and I will change the difference, right, all the states where phi 1 does not hold, right. Phi 1 until phi 2, I will check the states where phi 1 holds, I will check the states where phi 2 holds, and I will take their intersection, right, only those states where phi 1 and phi 2 both will hold, right. So this is how you can see that I am basically calling that same function, this is a sat, right, sat of phi. So this is how I will basically call recursively effectively, right. So if my formula is phi 1 and phi 2, effectively I will call this same function with phi 1, I will call this same function with phi 2, it will again recursively call this functions again, and finally it will return the states where phi 1 holds, right, and this call will return you the set of states where phi 2 holds, and then finally take an intersection of that, right. Similarly, if I have Ax phi 1, because I have only taken Ex, Af and Ex phi and Eu, right. So this is my adequate set. So anything not in here, I will rewrite them. So what I will do, because Ax is not there in my adequate sets, what I will do, I will write Ax in terms of Ex. So Ax phi 1 is basically nothing but not of Ex, not phi 1. So now I will call the same function sat with this formula, right, and again I will come back to this, and then if you see it is a not of something, so it will come into this line, right. Then here it will call the sat phi of Ex not phi 1, right. Again it will come here and it will come to this line because it is Ex phi 1, right. So this is how the entire things will go on, okay. Ex phi we have already algorithm, no, Ex phi. So this is the algorithm for Ex phi. So, I will basically whenever I got a formula from Ex phi 1, I will just call that function, not the sat, it is sat Ex, the algorithm is already defined. If it is E phi 1 and until, I already have the formula, I already have the algorithm, this algorithm, so I will call this algorithm effectively. So, I will call sat EU phi 1 phi 2, right. But if my formula is A phi 1 phi 2, which is basically, sorry, here phi 1 until phi 2, if phi 1 until phi 2, then what I will do, I will basically, because A until is not here, so I will rewrite this A until in terms of E until and EG. Okay. I will talk about EG because EG is something which also I will develop an algorithm. So, this is the equivalent formula, and I have already discussed why they are equivalent earlier. So you can just check that. So, what I am saying here, maybe I will just give you a little bit of idea. So, it is A phi 1 until phi 2. So, I am saying that either globally not phi 2 holds, there exists a path globally not phi 2 holds, right, because I am taking a negation of the formula, or not phi 2 holds until this holds, right, and I am taking a negation of that, and if this is not happening, then this will hold, right. So, you can cross check that. So, effectively I am calling this sat with this entire sub formula, and again it will come here and it will fall into some of the cases, it will call recursively and so on, right. EF phi, I can write EF phi in terms of EU, and this will be true until phi 1. So, I will call this sat function again for this, right, and then it will come back to this E until these cases, right. EG, now I am calling with AF phi, but I will develop a algorithm for EG subsequently. Okay. So, I represent EG in terms of equivalent formula, and then I call, next time this will come to this formula, right, because negation of phi 1. Then I will call sat with AF phi, and the next time this will come back to AF phi, this line, right. And for AF phi, we already have a formula that I developed here, this function, I will call this function, right. And for AG again, I will rewrite this in terms of EF phi, and EF phi it will come here, and effectively I will call this with here. So, first it will come to the negation of this, then from here it will come to EF phi into this line, and from EF phi it will call sat E until, right, E until phi 1. So, this EU already I have developed the function, right. So, this is the overall algorithm. Given any formula, it will basically call either it will convert into equivalent formula and then call these functions recursively, the same function, and finally it will return the set of states that where this particular enter formula phi holds, right. So, I already have discussed the complexity is AF into V plus E, and this V into V plus E is coming because of AF phi, right. If we can replace AF phi with something else, I can reach the complexity F into V plus E, right. So, this is what I will discuss now. So, if you just relook the adequate set possibility for CTL, you have set 1 where AX and E phi is there, set 2 where EG, AF and U are there, and set 3 is there. So, the rule saying that you take 1 from here, 1 from here and 1 from here, right. The example so I have taken so far is EX, AF, right. I pick this one and this you have to pick, right. So far we have developed algorithm for this, and problem with this AF, there is no problem with EX or EU. AF is complexity is high. So, instead of AF, if I pick EG now, then I will get the set which is EX, EG and EU, right. This is also an adequate set, but we will now develop an algorithm for EG, and we can show that EG I can calculate using B plus E, right, and then my complexity will become F into V plus E. So, effectively this will be the good adequate set for which I will able to have an efficient algorithm which is much more efficient, right. V into V plus E versus V plus E, one level short, right, one polynomial time efficient than the previous one, right. So, let us now see how we can develop algorithm for EG. So, so far we have discussed the least fixed point, right. So, basically what is happening, I start from set of states are 5 holes, then I add some few states, right? I am growing like this, then I add few more states, then I add few more states, and then I stops when one iteration does not include any new states, right? So, this is called least fixed point, right? Least fixed point. Now, think about, I start from the all states, right, and then I start excluding some states where that particular formula does not hold. So, effectively I am starting from the entire state space, right, and then I exclude some of the states where the formula does not hold, right. So, from here I am going here, again I apply certain rule and I exclude some of the states where the formula does not hold. So, from here I am going to the next set. So, I am now shrinking, right, and then finally I will again get a fixed point, right. That means after that I cannot shrink it further, and this is called greatest fixed point, greatest fixed point, right. This is least fixed point, this is greatest fixed point, okay, because this is the maximum, the larger fixed point possible, because I am shrinking the things, right. This is the terminology. So, this is what I am going to apply for EG. So, instead of starting from smaller state and growing, I will start from every state I am shrinking and finally get the final state, okay. So, let us see how I am going to do this leveling algorithm. So, I will start, I just mark all the state with EG, right. That is what I am saying, I am start marking all states. Then obviously, the states where phi does not hold, their EG cannot hold. So, I will remove all the states where which is not level with phi. From those states I remove level EG, which is very obvious. Then what I am doing, repeat until no change in level. So, what is going to happen? Delete the level EG from any state if none of its successor is level with EG, right. So, I take a states where I have already marked with EG, right, EG phi. Then I will see all of its successor. If at least one of the successor has EG, then it is fine, but if all the successor does not have EG, right, that means I cannot mark these states with EG, because what is EG? I found a path in which in all state G should hold, phi should hold. There exists a path in which globally phi holds. Now, I found a states whose none of the successor is EG, so I cannot mark these states also EG. So, I will remove EG from here, right. So, this is something I am going to do to remove states where EG already is level, I am remove them level, right. So, I start with all state. Initially, I remove the states where phi does not, the level is not marked with phi, it will shrink once. Then I will do this repeatedly, I will try to find a states whose none of the successor is level with EG phi, then I remove the level from this also, right. This will shrink. Again I will apply the same thing, I will keep doing it until I get a fixed point. So, now the question is, once you get a fixed point, how do you guarantee that it is actually EG phi holds here? So, now I found all the states. So, I basically get a set of states where at least one of its successor is EG phi, and it is true for this. For this also there is at least one successor which is has EG phi. For this also this EG phi true, for this also EG phi true. So, effectively they will form some cycle internally, right. And then that means for this all these states I will always find a states, I will always find a path in which phi holds globally, right. So, this is what the overall algorithm, but now as I mentioned, whenever you have to check one of its successor, you cannot do backward VFS, right. So, this is what we have already discussed, because what you have to do here, you have to check the states where EG phi is not marked. For EU we have done phi 1 until phi 2. In this case I start off the states where phi 2 holds, and then try to see one of its successor where phi 1 holds and one of its successor where phi 1 holds, and then this. So, but I have starting from with phi 2, but here I am trying to identify the states where EG phi is not marked, right. So, that is why I cannot do this backward VFS directly, okay. But if you do not do the backward VFS, your complexity will be high, V into V plus, right. So, then we let us come up with the efficient algorithm. So, what I will do here, this is just an efficient implementation of the same idea, the idea will remain the same. So, what I will do, I will basically only take the states where phi holds, which is very obvious. So, that is my starting point, and I will delete all the transitions and states where phi does not hold, right. So, I basically I have a states where phi does not hold. So, all incoming and outgoing transition I remove, because this cannot be part of this EG phi, right. By doing everything, I get subset of states where at least phi holds. That is my starting point, right. In this starting point, I will identify the strongly connected component. What is strongly connected component? You can think about a edge of 3, this is strongly connected component, because you can always find a path to go to another node in this graph, right. If you think about this one, this is also strongly connected component, right, which is basically you have always connections to your other nodes, right. So, I will identify the strongly connected component in this restricted graph, where phi does not hold and any edge coming to these nodes also removed. Okay. Now, from these strongly connected components, I can do backward VFS, right. So, I am interested to the backward VFS, which reduce my complexity. So, I will basically take a strongly connected component where what I am saying, all nodes have phi and they are basically forming a cycle, because you always can come back to any other states. So, they are strongly connected component, and in this state EG phi holds. Now, I will try to find out the states from where there is a transition to this SCC or strongly connected component, and this state where, because initially I have marked with, so the states I will identify a states where there is a transition here. So, then I will mark this also EG phi. Why? Because now I have found a path, because I have already removed all the states where phi does not hold, right. So, phi definitely holds here, and I found a path here inside where globally EG phi holds. So, here also EG phi holds, right. So, this is how I am going to do. I will stop when I will not able to add any further states. Okay. So, this is my FE state version. So, the key observation that it can reach a cycle consists of internally satisfying phi, that is your EG phi definition. So, I will identify the sets of states are phi holds. I will restrict the model to only those states, and then I will identify the strongly connected component here. And once, so Y SCC and SCC contains a cycle. Once the execution enter an SCC, it remain forever there. So, therefore, every state restricted to graph satisfy phi, phi can hold globally in this infinite path. So, EG phi must hold in an SCC, right. So, the overall algorithm as I mentioned, so mark all non-SCCs with EG phi, right. So, this is my EG phi. So, this is already marked with all the nodes here marked with EG phi. Then perform a backward VFS from here, and that is give me the complexity improvement, and I will identify states. So, the every state reached during this backward transfer I marked with EG phi, right. So, this is basically part of this now, and then I will do this, then again I will mark this with EG phi, right. So, this backward VFS I will do till I reach, I cannot add new states, right, and these are the all states where EG phi holds, right. And now, because I am doing backward VFS, the complexity will be order of V plus E. And if you remember, somebody who knows in algorithm, the finding strongly connected component can be done in V plus E, which is basically doing twice depth first search, right. So, if you are not aware of, please go through the context and understand what is SCC and how to compute that, which can be done in V plus E. So, now I develop an algorithm where SCC can be identified in V plus E, and this backward VFS can be computed. So, I can do it V plus E. So, overall complexity of this EG phi is V plus E, right. So, this is the algorithm pseudocode. So, I will mark all the states are phi holds, right, and then initially my X is null. So, until I stop this, because I am shrinking. So, I start with a null state, right. This is not this phi, this is basically empty, right, this is null. Okay. Then I copy this X to Y, all the states are phi holds, then I am doing pre there exist, right. So, effectively the states are phi holds, this is my Y initially, then I will identify a states where whose next state inside, and this is also part of this. So, I am not effectively taking a new state. So, I am basically taking a states here and identify there is a states inside there. So, I will keep this there and others I am removing, right. So, I am basically only keeping those whose successors are already inside, right. So, I am basically shrinking, it is not from outside. So, I am starting from here, I will basically remove some of the states whose successor is not part of the same state, I remove them, right. So, now I get this, then again I will get some states which successor is not part of these states and so on, right. So, this way I am basically shrinking and I am getting a fixed point, okay. And I mentioned the complexity is SCC is V plus E, backward BFS is V plus E. So, computation is V plus E, and if it will be multiplied with formula size, okay. So, I am able to develop the CTL model checking algorithm where the overall complexity is basically order of F into V plus E, and which is an efficient version. So, to understand that the model checking algorithm is basically efficient, right, then what is the state expression problem in model checking? The primary problem in model checking is not the algorithm, because we have already discussed an efficient algorithm, right, polynomial time algorithm. The problem is the model size. So, if this V has exponential number of states, then no matter even if this algorithm is efficient, it will be exponential, right, because you are searching in an exponential state space, and that is the primary problem with the model checking, and that is known as state expression problem, right. So, the number of states of a system grows exponentially with the number of system variable, right, and making this verification problem computationally exhaustive, right. So, you just think about that, you have 10 variables in your design or 10 flip flops, the number of state maximum possible is 2 to the power 10, which is 1024, which is quite big, right. Think about, instead of 10 there are only 20 variables. 20 is not a very big number, but which is basically 2 to the power 20, which is 10 to the power 6, it is a huge number of states, right, you can think about. And if you have 50 variables, which is not so uncommon in some design, it is 2 to the power 50, which is 10 to the power 15 number of states, right. Now, you think about the state machine which has 10 to the power 15 number of states. So, no matter how efficient your algorithm, none of them will work when your state space is this, right, and that is the problem with this model checking. In many cases, when you try to apply in a large system, if you do this way, explicit encoding of your states, you'll end up not able to do the model checking, because not of the algorithm, but because of the size of the model, right. So, this is what the consequences: excessive memory usage, long verification time, difficulty in exploring all state, and it basically limits the scalability of the model checking, right. But we will not stop here. So, we have to find out the solutions, right. So, there are many research happen here how to make these things scalable. Some of the things are listed here. One is called symbolic model checking. Here, instead of explicitly identify the M, what about the transition system which have, say, this many number of states, right? What about if I encode that machine as a BDD or a SAT formula, right? So, then I will not have a explicit state machine, but I have a BDD that captures the state machine, or I have a BDD that captures the I have a SAT formula that captures the state machine. Then this effectively what I am doing in this algorithm, it is basically BFS, backward BFS or forward BFS, right. So, this BFS, if I do on that particular BDD or a SAT formula, then I do not need the model which is exponential size, right, and that is what is called symbolic model checking, and that makes this model checking practically relevant and can be applied for very large system as well, right. So, in this course we will learn both BDD base and SAT base, encoding of this state machine, and how I can define this BFS and DFS on BDD. Those I will also discuss in this class. Okay. Also, you can abstract out certain things, so whatever not relevant, you can take an abstract model and check them, so that you do not need the explicit test space. You can also do compositional verification, like you identify components and verify independently, and then you abstract out this the detail, and then you verify the entire thing, right, combining this abstraction and compositions, right. That is also possibilities. And another important direction is bounded model checking. Instead of checking for infinite path, you think your paths are bounded by limit. In hardware also, although you think about hardware can run for infinite, but you can say if I am running for 10 cycle, I am confident that this output is correct, right. So, I can actually make a bound and I can do the model checking on that bounded way, right, and that is called bounded model checking. So, in this case the counter example will not be infinite, but have a given depth, right. So, we will also cover this bounded model checking in this course. So, in this course we will mostly cover symbolic model checking and bounded model checking, right. So, the key idea to tackle this state exclusion problem is that to reduce the number of state explored, represent the state compactly or symbolically, and decompose the verification task into smaller tasks, right. So, these are the two way of handling things, right. So, we will discuss those things in subsequent classes, right. So, with this we conclude today's class. Thank you.